CLI and a cross-platform IDE for C and C++. Download now.
Welcome, friends from all over the world. This is the long-awaited redux of the presentation, External Polymorphism and Type Erasure, a very useful dance of design patterns. My name is Eduardo Madrid, and as I was telling you, this is the redux because during the actual live conference, I had a multiplicity of inconveniences that prevented me from being able to do the presentation that you guys deserve. However, at least I tried to make it so that you could ask questions, because the real value of attending conferences is to ask questions. And the questions are useful both for the audiences and especially for the presenters, because it is the feedback that they get. Fortunately, I got some feedback, and I think I can do a better job for the Redux. Okay, my name, as you might know, is Eduardo Madrid. I will choose to introduce myself much later, because there's a point where it is something that makes more sense. What is the objective of this presentation? To basically see how useful type erasure is. The concept of type erasure and all of the programming techniques associated with it are quite technically intricate. And they have capabilities that are so powerful that our imagination does not match what they are able to do. So we tend to underutilize the possibilities, and from another side, the implementations of type erasure tend to be not good at all, and that blocks us from appreciating that we can do much better than that. So this presentation is a solution for those problems. The problem is that this presentation is going to be hard, but try to follow it. At least I think I have a very good system of breadcrumbs for you to re-inspect any topic that you might want. There is a Markdown document that has very good links to resources that explain things in greater detail, video links, etc. Okay, so let's get going. The first thing that I want to say about our subject topic of today is that this is a very unique thing to C++. Basically, no other language is going to allow us to work with something as fundamental as what are programming language features, intrinsic features in other programming languages. And in particular, I'm going to show you an example of a library or a framework done in user code that rivals successfully the very inheritance and virtual overrides mechanisms in the language. How is it better? Because it has better performance, and I can prove that objectively, and it also has higher modeling power. This is something that is on the leading edge. We will talk about capabilities we didn't know we have. So a reaction that you might have, which is legitimate, is that to think that this is all over engineering or solutions in search of problems. But that is a chicken and an egg problem, because if you don't know that something is able to deliver on some capability that will solve your problem, then you will not use it as a solution. And then when the solution gets articulated, it doesn't have the problem to solve, etc. Right? There is an intriguing feature that I'm going to tell you about. We can use the advanced capabilities of what I'm going to be talking about, because the real cost is not that you're going to lose performance, for example, but you're going to get more awful compilation errors, and it's still demonstrably better performance than code generation in terms of, let's say, object code efficiency. And it's very important that you know that most of this talk material is not disclosed elsewhere, not at all. So this is unique to this presentation. All right, the first hill in our journey that we have to climb is to really understand substitutability, a very technical concept. If we get substitutability right, then we have already succeeded partially. Now, everybody knows what a telephone is, right? let's say that you don't have a telephone, but you want to place a call. So there are several alternatives to you open, right? You can go and ask a friend that has a smartphone. And one characteristic of a smartphone is that they typically have no wires connected to them. They just use the wireless radio telephony or internet for that matter. Another choice that we have is that we can download an application that emulates a telephone, and then that'll be a virtual or an application telephone. We can also use an old telephone plug to a landline, and we can even use a rotary. I wonder at this point in time who uses rotary phones anymore. So, what is it that we're doing here? That we are not concerned with having a particular type of telephone, a concrete type of telephone. In our mind, what we have is an idea that is more abstract, that has less details about something that is going to allow us to dial a number somehow and establish a connection with the person that we want to talk to. So these type of requirements that we see in the real world are typically modeled in computer software with the technique of subclassing. It is the same thing that we know from the beginning of our C++ journey. It has a base class and an interface, a base class or an interface that has so-called virtual functions. I hope that you understand what virtual functions are, because if not, then we have a problem. But the point about those more abstract functions is that they can be replaced, overridden by implementations that know the specific details of the concrete type that are going to be implementing them. So one primary form of substitutability is achieved using the mechanism of subclassing. That part of using a base class and a derived class is called subclassing. Make please the observation that subclassing is suitable only for runtime. And for it to work, you need to have predetermined that you were going to need that subclassing capability so that you make all of your types adhering to the right base classes at the time that you're writing them. Because if you discover the need for some subclassing or substitutability later on, then you either will have to dramatically change the code or altogether do something else, because the change might be very disruptive of your workflow, the progress of your application. In that regard, it is intrusive that it gets into the writing of the software. It forces to make changes. You cannot have just a perfectly well-contained type. If you wanted to participate in subclassing, then you need to explicitly inherit from the right base classes. And that is something that changes the thing, only for the purposes of substitutability. Now that we saw the typical subclassing substitutability, it is very important for us to recover a different type of substitutability that is far more powerful. And I'm just going to introduce it to you through the example of a container iteration. So you can have iterators. And if you think about what we need in C++ to iterate over a container, it doesn't matter what the container is. You might want to have the equality and probably the difference operator. You might want to have a sentry to end the iteration, in particular the end iterator. You need the dereferencing to access the value of the container behind the iterator. You need to increment the iterators. And the things that I just mentioned are syntactical, but you also need the things that are semantical about traversal. Like, for example, if you start in the beginning and end in the end, you're going to traverse all of the elements in a collection or container. The good thing is that this is incredibly general. And this was great when you are writing the program that, for reasons, it is called compilation time. So we have substitutability at runtime when the application is running, and when the application doesn't know exactly what is, in the example of the telephone, what is the telephone that is going to be used, or the type of telephone that is going to be used to place a call. And you also have compilation time substitutability. So what is the essence of substitutability? That we can substitute a concrete type where an abstract concept is required and things just work. And this is the very famous Liskov substitution principle from Barbara Liskov at UCLA and so on. And the ability to make a such substitution is called polymorphism, because the poly part is there is multiple, and the morphism is the behavior. You can have multiple behaviors that depend on the concretions that implement the abstract concept in the substitutability relation, which is also called subtyping. Now, if we understand this, we have already accomplished a partial success, in my opinion. So, what are the pains of subclassing? Because subclassing is a technique that is used quite widespread, but it is very undesirable because it has lots and lots of problems. I believe that the person that has described the pains of subclassing the best in the history of our discipline is Sean Parent in his very brief presentation, Inheritance is the Base Class of Evil. I wholeheartedly advise you to, if you're on YouTube, for example, and you haven't watched this presentation before, please stop, because you need to watch this. And it doesn't matter what you do with my presentation, but Sean's is truly important. Now, I want to voice my own approach to the subject matter of the pains of subclassing, right? So I'm going to do something there, which is to summarize what Sean Parent explained much better than anybody else. But here we go. The most important problem is something that I never hear described to any degree of completeness. And my best recommendation for you guys to and gals to understand what is the real problem of subclassing for subtyping is to read a seminal article by Kevlin Henney that is called Value Conversions. You can see the URL in the slide. If push comes to shove, if you don't get this document, this slide deck, then you can type manually the URL. And I believe that his article begins with the question, how would you like to pay for that? And that is a very abstract concept, that of a payment, because it can assume a multiplicity of mechanisms and varieties of being realized that it is quite scary. So, two ways in which you can pay for things that's not even the tip of the iceberg, but the universe of mechanisms that you can use is to use money. And if you're going to use money, then what type of money, right? Like there are sterling pounds, there are United States dollars, etc. Maybe you're going to do some bartering. And the type of subtyping relations that you can represent with subclassing are quite limited. This is not the right presentation to go deeper into the subject matter. But again, I believe that this is the most important problem, how limited it is. Yeah, for that, I guess that you might have to wait to my presentation at C++ Now on the same topic. Another problem is that it's intrusive, as we had discussed before. And what is the problem with that intrusiveness? That perfectly well done types, like for example, an integer, the most basic int type in C++, has to be wrapped into a wrapper that inherits from the correct base classes. And this happens quite often, like for example, when we identify a need for substitutability or subtyping, typically like the many forms of serialization that many applications in many teams all over the world have attempted to serialize things in their own unique ways. So Obviously, the fundamental primitive type of an integer comes much before any user need to serialize an integer, because those needs tend to be quite different. And then there is the problem that you had to do all the busy work to wrap something like an integer into the wrappers. Another thing that I dislike about subclassing is that this is an intrinsic mechanism of the language that poses you with a challenge of take it or leave it. You cannot finesse this. You cannot play or modify the semantics or the syntax even of that feature in any way. And that's very restrictive, because we need to have multiple ways of doing things, because our needs are quite diverse. Then there is another chapter that is its own hell. I do not exaggerate by referring it to as a hell of that this forces referential semantics. So the problem is that the compiler, the language, doesn't know the physical or data layout of the things that are going to be subclassed. In particular, they can be a derived class that is far larger than any specification at the design phase. So the only way to deal with the fact that the layout of the potential subclasses is not known is by introducing one extra indirection. But that indirection is quite nasty, because it forces you to use allocations. And the problems of allocations are nasty themselves in terms of memory fragmentation and the crashing performance because of that synchronization when you have multiple threads. The mere fact that allocations might fail for quite a long variety of reasons, and then you're going to be forced to deal with a code base that fails more often. Then it poses you questions like when you make a copy of something that refers to something else as an allocation or dynamically allocated object, then are you going to do a shallow or a deep copy? And if you do, for example, a shallow copy because you can get away with it, then you have a problem of shared state. And these problems compound and compound and compound. One thing that Sean Parent mentions very clearly is that this disables local reasoning. So you cannot write code that is structurally sound, that guarantees at the level of the program architecture that things are correct. I was telling you that this incentivizes the sharing of a state. This is performance hostile in many ways. Like, for example, there's no runtime polymorphic way to indicate a data member. You always have to go through the invocation of a function. And well, that's expensive. So we really want to do much better than that. And what is the alternative? Well, we're going to go from substitutability to C++ templates. We're going to recruit the excellent capabilities of the language for compile time polymorphism and see if we can get away with mechanisms or a set of programming techniques that are going to give us runtime polymorphism without the complications, the root class of evil of using subclassing. It turns out that we can do it. So an important digression, and I promise you that this is not like in other presentations of mine that I have lots of digressions. This is the only one that I remember that I put. But this is truly important. Substitutability, polymorphism, runtime polymorphism, subclassing, and the scope substitution principle are basically the same thing for most programmers on any other programming language, and to some degree also C++ programmers. So it's just not acceptable, but because we are so different, C++ is so different to other programming languages, then people that come from other programming languages might be mistaken in believing that what applies to their primary programming languages also applies in C++. So if this presentation helps you in any way to realize that there are key differences between all of those things that I put in yellow, then the partial success of understanding substitutability is going to be improved um, much more by this realization. Okay. So the translation of compile time polymorphism to runtime polymorphism is what we're going to be calling external polymorphism. That means types that have nothing inherently polymorphic about them because it is not explicitly coded into them or whatever. We're going to write something outside of the types that we want to manipulate through polymorphism or substitution or subtyping. And these mechanisms are what collectively are called the external polymorphism. In the end, we're going to write to the solution of the virtual table. That seems all you need, except very advanced new possibilities that if the opportunity arises, I'm going to tell you at the very end of the presentation. So in principle, what we're going to be talking about are design patterns that are very familiar to most programmers, the decorator or the adapter. But you can use many others, including a strategy. It depends on exactly what you want to do. And we can see an example in the Compiler Explorer, or we can also go to the document that I have prepared to support this presentation. I'm sorry that I am scrolling through different windows without getting the. Seems that I don't have it in my browser, but this is a part of the repository or my Zoo libraries. The link is somewhere. There is a part of yes. So um, uh, this document is something that you ought to read on your own at your own pace and so on. It contains much more detail to help you recover understanding if I have dropped you in the video presentation, or if you want to know more about the things that I'm talking about. And what we're going to do first is to introduce external polymorphism has a form of an adapter using the adapter design pattern. And I think I have the link here to the Wikipedia adapter pattern. So, remember that the purpose of what we're doing is to give polymorphism to types that don't have it. One approximation that I think it is the approximation in the approximation of the approach in the book by Klaus Spiegelberger of Modern Design Patterns is this. We're going to say that we're going to turn things that are not serializable by themselves into something that is serializable by defining a handle, an adapter that is serializable itself. And see that I intend to use the subclassing mechanism. I'm going to explain to you that this is valid in a moment, but I'm just anticipating the objection. So I'm just telling you, yes, you are correct. This is using subclassing to avoid using subclassing in something else. And that's legitimate. So we defined an API serialized that has the signature that you can see. And we also give you the type index, because why not? And it has a virtual struct. All right. So we create the adapter root, and then we subclass the adapter with specific implementations that are called models of the adapter, because they model the adapter. And what we're doing is just to basically wrap a pointer to the type T, a pointer to the type T, whatever that type T is, can be an integer, for example. And now that we know that we are having a T, like an integer, then we can do whatever we want for the serialization. And the easiest to use serialization is to just use the streaming operations. So we insert the value that the adapter refers to into the output stream, and something similar with the type index. So I hope that this is relatively simple to understand. And by the way, this is the mechanism that Sean Parent used in his brief presentation, and he didn't need to go any further than this, because this is already providing the runtime polymorphism to things that didn't have it by themselves. And these runtime polymorphisms are less damaging than having to mess with good types, because these guys were made after the identification of the need for subclassing. But of course, this is not the best thing that we can do. We can implement external polymorphism without any subclassing. And the essence is described in this document, which is instead of an adapter, we are going to start with a concept that is going to be refined into implementations. And again, we put the same thing that we wanted before. So these are the functions that we want our runtime polymorphic interface to be able to invoke. And we can define some mechanism to bind the actual implementations to the concept. And because what we're going to be doing is a virtual table, I'm just going to call it a virtual table. And see, this asterisk here, this syntax that is very obvious, is actually a function pointer to something that takes an output stream and takes a concept, or a pointer to a concept. And this other function pointer doesn't even have arguments. All right. So the concept, the concept can have this type of implementation. It is going to have a pointer to its virtual table, and is going to use that virtual table every time that it wants to do runtime polymorphism, and it's going to invoke the correct members of the virtual table to flesh out the API that is trying to implement. And of course, it needs to have an object. This is the way that it refers to whatever it is that the object is referring. And we need to create we need to have a constructor that's going to take a pointer to an arbitrary type and make it so that that pointer is bound to the virtual table, and the binding between the object and the virtual table is what is going to allow the fleshing out of the different runtime polymorphic services. This would be an example for any particular type T. This is the thing that is going to generate a const expression virtual table for that. And this would be an example of such construct. I should not dive too deep into this code example because it's quite technical, and we are aiming towards the particular flavor of type erasure. We're aiming towards understanding why we ought to be interested in getting into this type of things. However, this compiler explorer document, this Component Explorer link or session already highlights a multiplicity of advantages of this approach. In particular, that the code generation is shorter. And the reason for why the code generation might be shorter is that you can do things like, for example, this is the natural order of the arguments on a binary API for the purposes of preserving performance. In the case of subclassing, then this parameter is implicit and would occur as the first argument in the list. So if you want to invoke something that is a wrapper for something serializable, the binary ABIs will have to swap the order of the parameters, and that is assembler that is completely wasted. It is code that needs to be there and occupy space for no good reason. And it even has a really small but still noticeable, and I have managed to do micro benchmarking that surfaces the performance difference between not having to rename those registers versus renaming them. And the situation of the code gen inefficiency is quite dramatic. Okay. This is the recapitulation, but I think that we can skip because I think it was comprehensively explained. So to conclude this part of the presentation, we ought to appreciate that the essence of external polymorphism is to give runtime polymorphism to types that don't have it. At this point, we are not concerned that the runtime polymorphism takes care of ownership. We don't want to have runtime polymorphism to own the objects. And if you remember in C++, owning an object means to participate in its moving and destruction and potentially copying. So, type erasure is the combination of external polymorphism when you want the runtime polymorphic services or APIs or affordances of destruction, moving, and perhaps copying. One very good example of type erasure is standard any, in the sense that the standard any only has runtime polymorphism for the ownership operations and nothing else, which is strange. And there are design errors that are fundamental to standard any. That's why it is not used, and I do not advise people to use the standard any. But you ought to understand what it does, how it does it, and what it's capable of doing, so that if you're presented with a better option, then you can lean hard on that better option and make a code that will be much better than anything else because of your understanding of type erasure. So the only way to do something useful with an standard any is to cast it to a concrete type. And the role of casting is fulfilled by the function standard anyCast, in which you tell the any, I know that you are, let's say, for example, an integer, so I want to see you as an integer. Much more useful is a standard function, because it at least allows you to have all of the type erasure functions for ownership and one anonymous function called signature. But it's a canonical example. It truly preserves the advantage of not being intrusive. And hear me out, you can have local variables of type standard function. Unfortunately, this is not going to be in the published, but I think it is important that I'm going to stop the presentation to highlight it. You can have local variables of type standard function, including function parameters. You can pass as a parameter the actual standard function without it being a reference or a pointer. You can also make them members. Another good thing about a standard function is that if it allocates, that is a fallback for some particular types that are too big or that have strange alignment requirements, and so on. The problem, alas, the standard function is a very bad design. And I am not criticizing the people that invented the standard function. Please do not understand that. That's not what I am saying. Douglas McGregor and the other people that collaborated on the Boost libraries to give to us a standard function years before other programming languages were able to do something like this is quite meritorious. They did something actually great. The problem is that was more than 20 years ago. Our community has failed to notice the problems and correct them opportunely. This is something that is becoming festering already. So what are some of those problems? Well, number one, it commits the capital sin of not respecting the single responsibility principle. Why? Because it performs type erasure like a standard any and a bunch of other things that is really bad. Like in my framework, the equivalent of a standard function is not a template by itself, but a template adapter. It takes something that provides all of the services of type erasure, and my subfunction limits itself to add to the instance the reference to the target, not to the target, the reference to the function pointer that will invoke the target in the right way. So my standard function doesn't do type erasure. It relies on some other data type that does the type erasure. In that regard, this template adapter respects the single responsibility principle, and that's one problem of how standard function doesn't respect it. Another problem is that it is not configurable at all. There is no way to indicate the size or alignment of the local buffer, the local buffer that is also called the small buffer optimization. It forces the targets to be copyable because, of course, a standard function predates move semantics. So copyability wasn't an inherent requirement of well-defined types in C++ at the time that the standard function was designed. And now it cannot be changed back. And even if we would not require copyability, as the case of Facebook's falling function. Well, sometimes you really want the thing to be copyable. The only solution is to be able to have both of them, like the move only to accept initializations or binding references from the copyable one. My framework is one of the few that support these, and the one that supports this infinite refinement in the most practical way. That's you're saying. There are all the things that you can see in the slides. Another problem is not. This is not a function. The name is quite misleading. This is a trampoline. And the difference between a proper function and a trampoline is that a trampoline tells you that you're going to jump. And so that is already a very conspicuous warning for the design of the call signature that you're going to get there. Like a standard function transforms all of the types that you give it into references, and that has its own performance drawback. Fedor Picus explained that drawback in his presentation, Type Erasure Demystified, a year ago here at C++ Now. And this is like an oversimplification to protect the user from misunderstandings that is not practical. There are many more problems, and I put that I need to stop because I can talk and exhaust the entirety of the time available for the presentation just on this point. I'm going to recruit Arthur O'Dwyer, the famous educator in the sphere of C++. He wrote this article that tells you the multiplicity of things that you might want from a standard function compatible library component. And one of them is considerations about the ownership, the local buffer configuration, like what I was telling you about the size of the so-called small buffer optimization and the its alignment, whether you're going to altogether disable heap allocation and make it a hard compilation error if you try to use it with types that would require allocations. What is the fundamental affordance set? Are we going to be move only, not even movable perhaps? What about the no acceptance and the constantness of the individual runtime polymorphic affordances? Well, what I want to indicate is that all of the things that Arthur O'Dwyer mentions are legitimate dimensions. This is the negation of the one size fits all. And then you cannot provide a solution for each individual thing because you want combinations of those individual things. The problem with the approach that we have been following is that the community drains itself discussing options that do not have a clear best. And we're missing the point, or our community is missing the point of how to make those choices available to the users. Perhaps the implicit assumption behind this flawed approach is the belief that it is impossible to make mechanisms that let the users choose. That's why we had to inspect that possibility in greater detail. Be as it may, because the true requirements of type erasure are so diverse, people are forced to redesign. Because this is so technical, then the redesigns are poor and the implementations even worse. This is a highly technical and misunderstood area, and my presentation attempts to at least show light on the problem so that more people get interested in solving it. And Arthur Dwyer actually falls way short of the vastness of the design space, the legitimate design space of things that you might want to do with type erasure. So I think that my conclusion about this is that rather than relying on the standard library to supply ever more species of type erasure fishes, we rather ought to learn how to type erasure fish ourselves. And the key of how to do it right is to understand the true complexity about all of this. We're going to get into the complexity in a moment. I just want to say that I am very honored that Fedor Picus chose to make the central point of his presentation on type erasure demystified a year ago, the performance techniques that I used for my own framework. But I am in disagreement with the very title of the presentation itself. There is not a demystification of type erasure. I believe, unfortunately, Fedor, there is an oversimplification about type erasure, a harmful one. So when I first discovered or noticed things like, for example, that a standard function didn't respect the single responsibility principle, my understanding at that point led me to conclude, I'm talking of 2017, that perhaps it could not be done much better. And to understand the roadblocks, I decided to set up on a journey of exploring that from first principles and see how far I could get. My discovery, number one, we are baking really, really deeply harmful and subtly wrong assumptions. And number two, the people don't really understand the theory behind it. What we really want to do, like the formal concept of substitutability and so on. And this problem leads to unclear thinking. And the unclear thinking makes it so that we don't get it right. We hurt ourselves. We think that type erasure is a technique that has costs that it actually doesn't have. It prevents us from seeing advantages and capabilities that type erasure does have, has impossibilities, and so on. Well, now I have a conflict of interest because I want this presentation to not be about the way in which I approach these problems. I want this presentation to be more neutral. But at the same time, I need to say that there is a solution already there that takes care of vast tracts of the problematics of standard function. And in particular, from more than 5 years ago, it allows the encoding, the articulation of entire proposals that have been accepted into the standard library since these, and these are just user choices in the case of my implementation. So I'm going to say something truly strong, which is that my framework doesn't even have just optimal performance. I can prove that the performance is optimal. A partial proof of these things is you can watch Fedor Pico's presentation last year of type erasure demystified. He goes over the significant mechanisms for performance preservation or augmentation. But there is much more than what Fedor mentioned, just like it's not as important. It's in my own work, especially of advocacy in public, like this presentation, I have already shown what my framework is able to do that goes beyond what any other can do. And well, the conclusion, the reason for why I'm saying this is not to praise my framework, it is to tell you guys there is a solution. And very importantly, I would be very, very happy if you reject my framework and try to do it differently. I have full intention of helping you as much as you want, of trying to help you as much as you want. And the reason is very simple. I know that I am just seeing the tip of the iceberg of what we can do with type erasure. If you come from an entirely different approach and achieve things that my framework cannot achieve, then there will be learning that is going to enhance my own understanding of these things, and it's going to make everything that much more productive. So of course that I want to help. And vice versa, if you want to help me in the development of these things, then perfectly all right. So feel free to contact me. So now is the right time to introduce myself, because I made a series of claims that well, it needs some support, because otherwise you're going to think that what I am saying is just empty talk of some crazy person that seems to have interesting ideas but have no relevance to the practicality of things. Because the most important attribute of what I want to share with you is on this part of continuing to do production code, things that get exposed to challenging real life scenarios, and continuing to get the type of extraordinary results that I have been getting. And that's the pedigree that I bring in terms of credibility for you to understand that, no, this is not something that is empty talk. So to begin to tie up the entirety of the presentation, I want to communicate with you that in the way that I have introduced these things, I made it so that a contradiction emerged that type erasure is sort of an internal external polymorphism. So external polymorphism is a standoffish way to give polymorphism to things that don't have it. Type erasure does that and also takes complete control of the target. By taking complete control of the target, it delivers on something that is absolutely wonderful, which is value semantics. And it gives us value semantics even if underneath there might be a reference. So another thing that is very interesting to me in general, not just about type erasure, is that the phenomenology of the emergence of complexity. That contradiction of internal external polymorphism leads to unpredictably interesting and useful behaviors that can only happen in the space that is in between contradicting design goals. One example of contradicting one example of the interesting things that you can do is that if you are assuming control of the owned object, so if you own the object, if you assume complete control of the given target for the runtime polymorphism, you can do whatever you want with it. And one thing that I could show you at a later opportunity is an already made implementation of a value manager that goes beyond the simple small buffer optimization or a normal pointer allocated on the heap. I think I have that already in the source code repository. So if we go to zoo, the tests, there has got to be a demo. This is the demo that I prepared for you guys. And that demo has, I'm just going to tell you, the shared pointer manager is that component, that will give you that capability. This is the entirety of what that value manager looks like. It will handle the value not has a simple pointer, but has a shared pointer. And you're going to see, I hope, that the use of that guy is very easy. Like, for example, a user any is something that is going to use an any container. This is the things made in my framework. But instead of using the normal policies that I wrote in the zoo libraries, this is going to be the user-defined shared pointer policy. And it's going to have a local buffer configured to be the size of 4 void pointers and the alignment of 4 void pointers. And it's going to have the services of destruction, normal movability, normal copyability, and normal RTTI. And here is a simple test case that illustrates that indeed some shared pointer is being used underneath. All right. We're getting close to the very end. We can do things that are much more radical. I don't want to overwhelm you, so I'm just going to leave the slides as they are at the moment. So I just want to recap that external polymorphism and the internal polymorphism of controlling objects, which is essential to type erasure, interact in very interesting and useful ways. And that is precisely the dance that gives rise to the title of the presentation. My outgoing remark is that if you feel that the advanced capabilities of type erasure are over-engineering, I have good news for you. I think you got important parts of this presentation because at least you know there are new things, the very things that you're skeptical about. I just hope that by the time that your imagination catches up to the capabilities, you still remember enough of their existence so that you can benefit from them. That's the very end. Thank you very much for your attention, and I hope that it's going to be of value to you.